Okay, very good. It's only been 4 minutes, but nobody's come through the door and everybody's signed in. So I think we're okay. Now I just realized that I've got a bunch of boards that are just all full of stuff. And some of that stuff you'll probably recognize if you're in the multivariable calculus class. You might want to have a little more to say about that. So I'm gonna clean the board, but in the meantime, here's a water pipe. You have a water flow. Is the velocity greater at this point or this point? So first answer that question. Let's call this A, let's call this B. Is water velocity greater at A or B? So just give me a quick answer if you know it. And then separately explain why you think that's the case. And we'll talk about it in just a couple of minutes. I'm going to clean off the rest of this board quickly so we have it available to us. Actually, that's the thing I wanted to talk a little bit more about, but we'll take care of that. Okay, now you don't want to watch me wash boards. So again, it's in the chat, type in greater at A, greater at B, and then if you have time, separately type in why you think so. Okay, now I've got responses. Everybody says the pressure is greater at B. Okay. Or says, I'm sorry, the velocity is greater at B. And most people say because the pressure is greater at B. That might be kind of natural, but let's make sure that we're doing it right. Now here's Bernoulli's equation. If pressure is greater at B and velocity is greater at B, which 3 out of 4 people told me, one person told me otherwise. If pressure and velocity are greater at B, what also must be true at B? If Bernoulli's equation really is constant. Go ahead and respond to that. I'll give you just a minute or so on that one, but see if you can give me a quick answer. See what you're thinking. All right, so I got 3 responses. The last one was kind of interesting. Last one said the density has to be smaller. Okay, well, if the density is smaller, what's going to happen to this term and what's going to happen to this term? They're both going to get smaller, right? If P and V are greater, then what has to happen for something to be constant? Well, in the first place, and you would get this out of the introductory problem sets, if you achieve the level of mastery that we need to get, there's a very specific problem that says, basically, if something goes up, something else has to go down. So that's certainly density gets less, that could accomplish it. Because if P and V are both higher, a lower density could keep things constant. And that should be obvious. And if it isn't, ponder it and work it out with some numbers, okay? Now, in this case, what we've got is water, okay? So density could be lower. That's good. But water is incompressible. But that's not so if the fluid is water. It can't be so, even though that would answer the question. Now, not every fluid, air is a fluid. You know, gases are fluids because they can flow. Liquids are fluids because they can flow. Fluid is something that can flow. If it was air in the pipe, and I'm not sure I said that it was water. I said we got a flow in the pipe. I might have said water, but if it's air, then it would be very possible for the density to be different at the 2 points, and that might be an explanation. Now, in this course, we're not going to deal with fluids that don't have constant density, simply because we're not going to go that deeply into fluid mechanics, okay? It's kind of the next step, and it can often be done in this course. It might even come up. But so that's a very good answer. If this is not an incompressible fluid, it's a possible answer. Okay. Now, other answers that I got. One said the diameter tube has to be smaller, although that's given. We know that the diameter of the tube is smaller. And actually, maybe I had 4 responses and I was waiting for no good reason. My window here isn't showing me as much as I'd like. One said B increases velocity and lower pressure. Okay. So if we increase the velocity, this gets bigger. That would decrease the pressure. I mean, if we do decrease the pressure, that would take care of it. But I said if P and V are both greater at B, then what would happen? Now, to say that the velocity is greater here than it is here, yeah, we're going to see why that is. Or you're going to tell me, okay, the velocity is greater here than it is here, and that tells you what happens to the pressure. Another response I got was diameter tube must be smaller. Said rho GH must be proportionally smaller. Okay, and that's correct. If both this and this go up, this has to go down by an equal amount. So that said, rho GH decreases to balance the left-hand side. I should have really said keep the left-hand side constant. So I'm going to change my word there, keep left-hand side constant. Okay. So that's really what goes on. Now, again, in the introductory problem sets, there was a problem that asked in a variety of different ways, what happens if one of these things goes up? Well, if one of these things goes up, the total of the other 2 has to go down. If 2 of these things go up, the third thing has to go down. And that's the key. Now, why is it that the velocity increases? If this is an incompressible fluid, then let's just consider how much fluid passes, where's my blue chalk? There it is, passes this point. Which is let delta t be some small time interval, then the volume passing this point has to equal the volume passing this point. Since the tube is narrower here, you're gonna have to flows are gonna have to be extend greater. So that the volume here is gonna spread out here. And it should be clear that since you've got a lesser cross-sectional area, the volume here has to be greater than it is here. Now there's a continuity equation. If you want to use an equation instead of understanding what's going on, and you know, if you're real bad at, I mean, if you're strength, you're not real bad at, nobody's real bad at anything. But if you're, now I lost my train of thought. If you understand a formula better than you understand a picture, you might prefer to start with a formula and develop the picture. But one way or another, you really need to understand the picture because the formula can get confused. Okay. Even if you got 100% recall, you want to have at least two ways to know anything, which is formula, picture. For most people, you want to start with a picture. It all comes from the concept. An incompressible fluid, the same volume in this part of the tube is going to have occupy a longer section of the tube than an equal volume in this part. Okay, so okay, delta x over delta t is greater in the smaller tube, so the velocity is greater. Therefore, this and or this have to change. H, well, I've drawn this thing horizontal. H doesn't change. So pressure has to go down. Now, I'm not going to write out the rest of that because it's all there in the introductory problem sets. I recommend that you go to the second set, the one that has an XPV in the name, and you have multiple problems. These problems are not always stated the same way in the part that has the solutions as they are in the part that has randomized problems. You don't get the same numbers and you don't always get the same statement. Okay, so you really should read each problem. You know, read through these problems once a day. Read through the problems that you aren't given a solution to, and just in your head say, okay, I got to do this, I got to do that. And then every once in a while, work the things out, or at least the ones that aren't completely obvious. And some of them certainly are completely obvious. Make sure you're thinking correctly. You can always go back to the given solutions and check your thinking. Think them through without looking at the given solutions and without having looked at the given solutions for 24 hours. Incidentally, the assignment for Monday, and I think there's going to be somewhat of a text assignment too that I haven't posted yet, but the assignment for Monday is going to be to really have the entire set mastered. And I want to talk about more of the set, but I want to talk about how you use the set, okay? How you use the problem set. Incidentally, if I'm up here looking like I'm explaining things and you're not hearing anything, actually, you would be hearing it. You wouldn't know I wasn't recording. Anyhow, it's recording. Okay. Now I want to go on to kinetic theory. And I'm not sure how well this is going to work. I don't have quite as much room up here as I'd like. And I can really demonstrate this nicely on the tabletops. But let's just see what we can get. I also know how to do this on the tabletops. Up here, I haven't tried it, and the angle's a little different. But I'm going to drop a ball. Now it's a pretty good ball. Okay. I almost didn't catch it because I was looking at the screen, then I realized, oh man, I got to go look. Okay. Now what I'm going to do is I'm going to drop the ball and I'm going to lower this tile. Oh, bounced out the wrong way. Okay. Try again. Okay. Hopefully you could hear that. The ball started bouncing back and forth very quickly. Now that makes a good demonstration. If I do it in the tabletops, I don't really have a good way to get the picture all the way down to the tabletop. But what's happening? Why does the ball make the noise it did? I hope you can hear it. Pretty sure you can. Okay. Well, two things are happening there. Every time this thing that's going lower and lower hits the ball speeds up. That's simply, we can treat it as though it's an elastic collision. Now it isn't. You probably want to look up the term coefficient of restitution. Probably we get 90% of the kinetic energy. And we can kind of test that. If I drop a ball from here, question is, how high does it go? Oh man, that didn't go anywhere. That's a bad ball. That's better. Okay, what about here? It looks like it bounced back to about 80% of the height from which I dropped it, maybe even 85%. It will pretend it's 90%. Okay, so what's going on is, here's a solid surface. Here's a ball. It's dropping. Here's a massive object. We'll treat it as though it has infinite mass so that the ball rebounds with 90% of its relative velocity. Okay. Now let's focus on the tabletop or whatever this happens to be. Means every time it hits here, there's a change in its momentum. So we have the impulse momentum theorem. Okay, impulse momentum says change in momentum is equal to the average force multiplied by the time interval. Okay, so we have delta P equals average force times time interval. Now we're going to switch to the ideal case because this is how we begin to understand the nature of the forces exerted by a gas to create pressure. Now in this example, we are looking at water flowing, and water consists of chains of molecules essentially that are twisting and turning around each other, okay? And not individual particles akin to plastic balls, okay? One other thing I'll say about this, since I've got one of these things right here at my feet. In a monatomic gas, everything can be modeled up to a certain extent with a certain amount of precision as single balls bouncing off of one another. Okay, so let's get two of them, you know, they can bounce off of one another. I can toss this one up and hit it, but they'd be outside the camera. So have a 1 in 100 chance of hitting it. So you start with the idea of a ball hitting a surface, okay? So the molecules in a container, molecules in a container of air, some of those molecules are going to be monatomic because there's some hydrogen and some helium in the air. And when they hit a wall of the container, they behave in a manner very similar to this. If you have diatomic molecules, which make up the majority of air, oxygen and nitrogen together make well over 90% of what's in the air. So air is essentially mostly diatomic. You could even have polyatomic molecules. They behave a little bit differently, but there's still a change of momentum when they collide with the walls of the container. And we'll see how far we can get with understanding that. Now, all that is addressed in the introductory problem sets at a very basic level, but we want to build on that. I'm not sure I've got a side of this board. So we're going to start with the model. Let's say we've got a piston in a cylinder, and we got a molecule of mass M. With velocity V parallel to the axis, so that it's perpendicular to this side and this side. Elastic collisions. And you want to kind of review all that from first semester. Now let's see, I see something here. Oh, there's a new message. Hang on. I can't see. Don't know how long that message has been there. Oh, somebody mentioned Venturi effect. Yeah, that's exactly what was going on with those tubes. So you want to look up Venturi effect. It's in your text. You should. I'm going to give you, chapter to scan, tell you what to ignore. We're not going to be able to do much with viscosity or surface tension, but we'll mention them. But we kind of focus on Bernoulli's equation and its consequences. Okay, back to this now. We're done with fluids for the moment, but of course we're still doing it. What's the average force on the end wall? Okay. Now, I'm not going to ask you for a response because we want to talk about a lot of things here. But you should make sure you understand impulse momentum well enough to answer this question. Okay. The average force on the end wall, well, change in momentum is negative 2m times the velocity vector. So here's the velocity vector. On this end wall, the velocity is going to go from positive to negative without any change in speed. So that your net change of momentum, well, momentum is mv going in, and it's going to be the negative of mv coming back. And the difference between mv and negative mv is 2mv, negative 2mv. That's the change in momentum. Change in time is, well, we're going to take a second. I'm going to see if anybody can tell me quickly what the change in time is. I'll give you about 30 seconds. What's the change in time between the collision here and the next collision here? Ball's got to go here, back, it's got to go back and forth before it collides here. So in terms of V and L, the only things you have, what is the change in time between collisions? Go ahead and enter that. Anybody has a good answer? Even a bad answer. Okay. Delta T equals distance over speed. Okay. Between collisions with that end, delta T, distance over speed, which is 2L over V. Now, what's impulse momentum theorem say? Delta P is F average delta T. Now, the answer I got was 2mv over F. Well, that would be delta T. So that's not a bad answer to delta T, but at this point, we don't know what F is. Okay, so if you want to find F, this is how you use the impulse momentum theorem. So that average force is your delta P, which is negative 2m times the vector velocity, because momentum is a vector, but then divided by your distance over speed, 2L over V. So it's negative mv times v without the arrow over it, divided by 2L. Magnitude of F average is then negative mv times v over L, which is negative mv squared over L, which is negative 2 times the kinetic energy over L. I'll use KE here, so don't confuse it with an arbitrary constant. Okay, so we have kinetic energy here, and this says that the force being exerted on this end is proportional to the kinetic energy of the object. A bigger mass with a smaller velocity will have the same impact on the end as a smaller mass with a bigger velocity. So if you got different kinds of molecules here, it's going to turn out that they all have the same kinetic energy. I will talk about that in a minute. They're the same average kinetic energy. Their kinetic energies are all over the place. So, well, there it is. That's for one particle moving along an axis. Now, one particle in a random direction. With the speed v, you get v squared equals vx squared plus vy squared plus vz squared. The average, I'll put a bar over these are not arrows, they're bars. Vx bar squared, vy bar squared, vz bar squared. These are the average velocities in the x, y, and z directions. Okay. Now, I said these are random directions. We'll see why they are ultimately going to be random directions. And actually, the answer to that is if I've got a bunch of these things bouncing around there elastically so that the total kinetic energy remains unchanged, then they're going to start hitting each other and the directions are going to become random. Okay. So we have average x velocity equals average y velocity equals average z velocity. So we have v squared is 3 vx bar squared. Now, if we have a bunch of molecules, I'll just say multiple particles. Directions are random and average velocity I'm going to say multiple identical particles. Directions are random, so average velocity is constant. V bar. So we have V bar equals 3 Vx bar. Sorry, V bar squared equals 3 Vx bar squared. So that average velocity is 3 square root of 3 times the average x velocity. Also square root of 3 times average y or square root of 3 times average z velocity. Right now we're concerned with the x velocity because implicitly the x direction is the direction of the axis of this cylinder. And it's only the x direction that causes a momentum change at this collision. Okay, so if a ball comes in at this direction, the ball comes in here, it hits and rebounds at an equal angle because of conservation of momentum. The y and z directions don't change on an ideal collision, and these are ideal collisions. Okay, average x and y velocities are unchanged. I'm sorry, the average y and z velocities are unchanged. Only Vx changes. Okay, so here we have Vx. And here we have negative Vx. Of the ball when it's here. So that change in momentum is negative 2 mvx. And delta t is 2L over Vx. And at this point, I'm going to put average here. So on the average, the change in momentum of a particle, of a single particle, is negative 2m times Vx. If we're talking about a collision on this end, then Vx is in what we might regard as a positive direction. So rebound in the negative direction. So we get delta t is 2L over Vx average. And that's average delta t. So that average force and I'll put an X there, Fx average is going to be negative mvx average squared over L. Same expression we had up here, except now we're just talking about what's going on in the X direction. So it's negative 2 times the X kinetic energy divided by L. See if we got any comments or questions. Yeah, appended to the last negative 2 mv over F, and I acknowledge that you know, that was good because you were definitely using this equality here, but you were solving for delta t rather than using delta t for solving for F, and you clearly could have done that. That was good. Okay. So what do we have now? Well, if we have capital N particles, the average X force is N times its brake. So we put a bunch of these little balls, or a bunch of molecules that actually do collide elastically, into the container. We give them some energy, and they start bouncing around randomly. The average force on this end is negative 2 times the average kinetic energy, and it should be the average kinetic energy. I'll put a bar over it. An average X force on that end. Of course, that equals the average force exerted. Yeah, I better not say that. I better not say that. It occurred to me, seemed like a good idea. Thought I'd write it. I'll just observe that the average X kinetic energy, average Y, and average Z kinetic energies are all the same because the directions are random. So that average Vx, average Vy, average Vz equals are all equal. Okay. The average X kinetic energy is 1/3 the average kinetic energy. In other words, V squared is 3 times the Vx squared. So the average kinetic energy based on V is 3 times the average kinetic energy you would get based on Vx. So the average X force, negative 2/3 N times the average kinetic energy over the length of the cylinder. Now, average pressure is average force over area. And hopefully this is starting to click a little bit. Just let A sub CS be the average cross-sectional area. And the average pressure is well, you're going to divide this by A, which is going to give you an A in the denominator here, which is then negative 2/3 N. Well, pressure is a magnitude, so we're going to throw away the negative sign. I'm kind of waving my hands over that, but think about it. Okay, there's your average pressure. What do you get if you multiply the length of this cylinder by its cross-sectional area? You get its volume. Well, that gives you pressure times volume is 2/3 the number of particles times the average kinetic energy. Now, empirically, PV equals, that should be capital N, okay, where N is the number of particles. And you've almost certainly seen that before. If you haven't, you've certainly seen this before. Lowercase n times RT, P equals nRT. Now that's what we get by observing gases. This is what we get theoretically. Now, N, capital NK equals little n R. And I'm out of board space and I really want to make some profound comments here. Let's see what we're going to do about that. Okay, I'm going to pause the video a second.